so number one on this started you out with a table, and it has a little bit to read, and the stuff that you read is actually super important. When you're reading FRQs, kind of like when you read the directions on the quiz and it asked you to write a smiley face, sometimes things like that are important. The smiley face, not so much, but sometimes they are. For instance, in this problem, it says the functions f and g are differentiable. Now that's a little word. Usually we skim right over that, but it's actually kind of important because of what I wrote on the board over here. So if you're watching this recording, you don't know what's on the board. So it says, if a function is differentiable, then it is continuous. If you can take a derivative of it, if it's differentiable, then it is continuous. However, that doesn't work in the reverse way. A continuous function does not have to be differentiable. Case in point, absolute value. All right? So if a function is differentiable, like it says this one is, f and g are both differentiable, we know that both of them are continuous. So that's a read between the lines to figure out if your theorems can be applied situation. So they are often going to do that to you, and you have to know this implication. G is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by all of this. All right, so first it says, explain why there has to be a value r on the interval 1 to 3 such that h of r equals -5. All right, so this is talking about h of r itself. So we have some theorems to choose from, and if you guys read that, it kind of looks like it's setting you up for a theorem. But which one? This is IVT, because IVT involves regular old functions, typically. Could you use IVT with a derivative? You have a graph of a derivative. Can you use IVT to say that there's a value in between here and here on the derivative? Sure, you can. So that doesn't always work, but if you see a regular old function, I would think IVT first. So if we want to use IVT, or at least try it out, there are some things that we set up. We listed them on the board. We also put them on our pink sheet. We have to state that the composition is continuous, and I did that by saying that this is a composition of differentiable functions, so it's going to be continuous on the closed interval. College Board, whose answer is here, College Board doesn't even say that. It says h is continuous. That's it. The end. No paragraph, no explanation. It just says h is continuous. So this is a situation where we have the benefit of seeing what College Board is looking for before we actually finish a question, but I would always write a little bit of thought. Maybe you don't have to. I've never seen it, but sometimes it's nice just to hedge your bets there. So h is a composition of differentiable functions, so it's continuous on the closed interval. Then we talked about we want to evaluate each of those functions at those points. So to evaluate that, we have to use this long composition with the -6. Just write it down, plug in your numbers, take it one step at a time, show your work neatly. We end up with 3 for h of 1 and -7 for h of 3. So we've done that part, but we also have to say that the -5 we're looking for is between those two values. So all of this straight from what we've written on the board. Okay, we're just following that formula. Because this is checked off and this is checked off, we can state that by the intermediate value theorem, and then I use some notation that you may or may not be familiar with, but it's a shortcut. This says, so by intermediate value theorem, there exists an R in 1 to 3, this is actually an element of the interval 1 to 3, such that h of r equals -5. So this is what we want to write as our conclusion. Again, straight from the board. So you guys did really well on your theorems on the quiz, and I'm hoping that you'll continue to study those so that if you see another problem like this, you'll be good to go. Any questions on that part of that problem. Okay. For the second part, it's a little bit different. It says, explain why there has to be a value c for the interval 1 to 3 such that h prime of c equals -5. Here we are looking at h prime. So that implies MVT. Maybe it'll work, maybe it won't. We'll check it out and see. To set up MVT, we have to talk about differentiable on the open interval, continuous on the closed interval, and we have to then find the average rate of change. So once you've set up the continuous and differentiable part, you can just find that average rate of change. Make sure it's what you're looking for. So if this wasn't -5, like it asked us for in the question up here, then you'd have to take another route before you rule it out completely. So h prime of c equals -5. We just use MVT, found the average rate of change is -5, and that's what MVT says. So that's how we check that off our list. Any questions on the second part there? Yes, Nina?
So if MVT doesn't give the same answer, is it not a possible value?
Great question. So we'll see something like this in a little bit, but if MVT didn't give me the actual value, would I be able to find the derivative of h and see if I could do an IVT situation? Like find h prime at 1 and find h prime at 3, and then see if h prime was in between, like -5 was in between those. Maybe so. But if I were finding h prime, I'd have f prime of g of x times g prime of x minus 0. And so I'd have to know g prime and f prime at specific values that may or may not be in this table. So it's a matter of information. But since MVT worked for us, we don't have to go into that too much, but it doesn't necessarily mean that absolutely not. Great question. All right. Speaking of, on number 2, we've got Ben's unicycle ride. And this is one of those problems that kind of, again, makes you read and makes you think a little bit more. We're riding a unicycle for some reason on an east-west track. The twice differentiable function, which again implies continuous, so reading between the lines, that is important, models Ben's position on the track, measured in meters. All the units are buried in here. The table gives B and Ben's velocity, so the derivative of B, measured in meters per second at selected times. On the interval 0 to 6 or 40 to 60, there be a time when Ben's velocity is 2 meters per second. So if we're thinking about a velocity for Ben, we've got velocity numbers in here, and we've got Ben's position in here. So which theorems are available to me? Could I use MVT? Do I have information to use MVT? Sure. And this is talking about his velocity, so that is a prime, so we've got an instantaneous rate of change, and we can find the average rate of change using the table here for B of t. Could we use IVT? Do we have information that we could use IVT for? So for IVT, we would have to do the velocity at 60, the velocity at 40, and say, okay, 2 meters per second is between those. But is it? Is 2 meters per second between the velocities of those two times? No. So if you're not careful, you say, oh, IVT doesn't work? No, there's no way he could get there to a 2 meter per second speed between here and here. But all we have here is a snapshot, an instantaneous picture of what he's doing. There's no telling what he does after his 2.5 meter per second velocity. He could fall off his unicycle and get back on in that time, which means he would cross the 2 meters per second mark. So we don't know what goes on between there. Maybe he does, maybe he doesn't, but we don't have proof that he does. So we try MVT instead. And MVT says that the average rate of change is equal to the instantaneous rate of change. So if this instantaneous rate of change equals that average rate of change and it is 2 meters per second, then we can say conclusively that yes, Ben is going to hit 2 meters per second somewhere on his ride. between 40 and 60 seconds. Okay? So that one was one that a lot of people ruled out just because it didn't work with IVT. So, any questions on that? All right. So let's look at 3. This one was uber tricky and uber popular in College Board. Super, super duper popular. This relationship where we are subtracting 2 rates to find another rate comes up an awful lot. And most of the time, they don't give you this rate to write down. So you have to figure that out. So a couple things that are important in this. We've got rain accumulating in a cylindrical can, which makes you think related rates, but we hadn't, doesn't apply here. Can's empty, it's entering over a 60-day period. Height of the water's modeled by S, measured in millimeters, and the rate at which the height is changing is S prime. Then it goes on to say the height of the water in the can can be modeled by this function M, and it gives you the function there. So we've got 2 cans that are identical to each other, and stormwater's accumulating in them at different rates. One in Stormville, one in Monsoon Mountain. So not places that I would settle most likely, but still. So I kind of highlight things, write down notes or whatever. This says we want to know if there's a time when the heights of the water are changing at the exact same rate. So water's filling this can, water's filling this can, different rates, different amounts, but is the rate ever identical? And D of T represents the rate in Monsoon Mountain minus the rate in Stormville. So if we want to find when those are identical, we want to know when M prime of T equals S prime of T. Does everybody agree with that? The rates are the same. If M prime of T equals S prime of T, what do you get when you subtract up here M prime of T minus S prime of T? 0. Okay? So they didn't actually come out and tell you that we're looking for where D prime equals or D equals 0. They didn't say that. You had to reason through that, and that comes up a lot. So we want to know if D of T is going to equal 0 ever on this interval. So you have to set up the continuity. You have to set up, well, only that in this case. And we've got to calculate D of 0 and D of 60. So find the rate that we're at D of 0 and 60 seconds or time or whatever. What's the time on this? The water, blah, 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 blah. Days. So at days, 60 days, 0 days. So we find this for 0 days, this for 60 days. We know they're both differentiable, therefore continuous. So there is going to be a point in time where we hit 0 in between those two. So we can say that, yes, the rates are going to be changing at the same rate by the intermediate value theorem. So this one is very complex, very layered. You do have to use a calculator, and if you do use a calculator, it actually goes pretty quickly because you can take the derivatives of both of them. I won't say quickly, but it's not that bad. Any questions on that one? Zane?
So like when the College Board gives us problems like these, do they usually tell us what theorems to use?
Usual is a tough thing to quantify. I can't say yes or no to that because if I say either one, they'll do the opposite of what I say. So I would just know as much as you can, practice as much as you can, and you'll be as prepared as you can. Another thing to mention, I think I've mentioned this before, College Board does not expect you to get 9s on every FRQ you take to get a 5. In fact, if you make a 5 on all of them, you'll make a 5 easy. So you can always miss some questions. So all that to say, even on our tests, if you feel flummoxed by something, don't throw in the towel. Because if you can just get a few points here and there, you can get a 5, which means you can get an A in this on the test in here. So just do as much as you can, and we'll be good. Any other